Now this week we will continue with the two-variable regression model, the problem of estimation. As noted in chapter 2, our first task is to estimate the population regression function on the basis of sample regression function. So from our population, we know that we have two parameters, intercept and slope parameter, beta 1 and beta 2. So we are selecting different samples in order to estimate the population parameters from sample. So we are estimating beta 1, estimating beta 2 from sample 1. So we can select another sample. Again, we can obtain the population parameters by using ordinal least square estimation. So we can select infinitely many samples from this population. So this is our main methodology while we are estimating the sample parameters in order to find the population parameters. So we can estimate beta 1 and beta 2 from the end sample as well. So these are nearly similar kind of estimation. The estimation quantitative results are very similar to each other. So we will see how we estimate beta 1 and beta 2 in this chapter. So the name of the chapter is the problem of estimation. So what kind of a tool we can use while we are estimating beta 1 and beta 2? So the first important estimator is ordinal least square. So for the more advanced estimator, we can see maximum likelihood estimation. By and large, it's mentioned of OLS that is used extensively in regression analysis, primarily because it's intuitively applied and mathematically much simpler than the maximum likelihood estimation. Besides, as we will show later in the linear regression context, the two methods generally give similar results. So this is a simple methodology, but it will give the same result with maximum likelihood, which is more advanced methodology. So we will continue with the ordinal least square. The method of ordinal least square is proposed by Carl Friedrich Gauss. There is, under some certain assumptions, the method of least square has some very attractive statistical properties that have made it one of the most powerful and popular methods of regression analysis. First of all, we have to understand what's going on with the ordinal least square. So recall the population regression function. So the population regression function, we write this equation yi equals to beta 1 plus beta 2 xi and a stochastic term. So population regression function is not directly observable. So we have to estimate this population regression function by using a sample regression function. So again, recall from chapter 2 that sample regression function is yi beta 1 hat plus beta 2 hat xi and a residual term or error term. So this part beta hat and beta 2 hat can be written as y hat plus u hat. So this is a simple algebraic manipulation. So y hat is estimated conditional mean value of yi, but how is the sample regression function itself determined? To see this, let us proceed as follows. First expression 2, 6, 3. So yi is this is the actual yi minus estimated yi. So the residual can be obtained by using this formulation. So if we use this part, so yi beta 1 hat minus beta 2 hat xi. So let us see what's going on with this estimation. So let us see from here. So this is yi and this is y hat. So this is ui1 or ui. Ui is equals to y1 minus y hat 1. So this difference is the residual term. So for the second one, for the third one, for the fourth one, we obtain this deterministic part of the sample regression function. So these are all estimating beta 1 of population and beta 2 of the population parameters. So first of all, we have to think about what is the principal idea while we are deriving the principal idea, driving the OLS estimator. So in this case, we have to find a distance by drawing this linear regression line, which is passing, and while it's passing, it's creating the minimum distance between the residual terms. So this is our principal idea. We are drawing the line to obtain minimum distance. So in this case, for example, sample regression function 1, we draw the line and we obtain u1 distance plus u2 distance, u3 distance, and u4 distance. So we have to add these distances to each other and obtain a distance 1, for example. Let us draw another one with this is 0.1, 0.2, 0.3, and 0.4. For example, this will be like this. Sample regression function 2. So we will obtain this distance for the first one, u1, plus for the u2 this distance, for u3 this distance, and u4 this distance. Distance 2. So the main principle is, let us draw with black one, distance 1 bigger or smaller than distance 2. This is our main question. If distance 1 smaller than distance 2, Then we select sample regression function 1. Or vice versa. Which one is more smaller than the other one? Then we are selecting the smaller one. So in this case, most probably sample regression function 1 is smaller than, creating smaller distance than sample regression function 2. So most probably we will select sample regression function 1 for this sample, for this example. But in this case, for example, when we look at the U1, U2, U3 and U4, most probably this is positive, this will be positive. Let us make them in red. This will be positive distance because it's, when we subtract Y1 from Y2, we will obtain a positive distance. When we subtract U2 from U2, minus 2 hat 2, we will obtain minus distance. So this will be minus, this will be positive, this will be minus. So nearly U1 and U4 is similar distance, but one of them is positive, one of them is negative, so they will cancel each other. U2 and U3 are similar to each other, so there will be a cancellation between these two as well. So we will come to a conclusion that the distance will be 0. In order to obtain a positive distance, we have to take square of these distances or absolute value of these distances in order to find a positive distance while we are obtaining the residual terms in this calculation. So let me show a general formulation for this. So in this case, from I1, the first observation, to end observation, we are obtaining UI square. So UI1 square, UI2 square, U3 square, U4 square. This is the compact formulation for showing this open formulation. So this is a compact formulation for this simple formulation. So we are making an optimization. So what is the determination of UI? UI determined by beta 1 and beta 2. So for this beta 1 and beta 2, we are obtaining this one. For example, for this sample regression function, we will obtain different set of beta 1 and beta 2. So the minimum value of the distance is obtained by using beta 1 and beta 2. So we are taking the partial differentiation of beta 1 and beta 2 in order to see the minimum distances. So we will get a partial differentiation for beta 2 as well. So if we obtain the efficient or optimal beta 1 and beta 2, we can obtain these two normal equations. This is normal equation 1 and this is normal equation 2. Then we can obtain a formula for beta 1 and beta 2 as well. So in this lecture we will see this short summary explanation by using extensive explanation of the methodology. So let me We shows the UI are simply the difference between the actual and the estimated y values. Now, given m pairs of observation on y and x, we would like to determine the sample regression in such a manner that it is as close as possible to the actual value. So, we are searching for a manner or behavior that it is as close as possible to the actual value, y. To this end, we may adopt the following criteria. Choose the sample regression function in a such way that sum of the residuals, this one, sum of the residuals, is as small as possible. Although intuitively appealing, this is not a very good criterion, as can be seen in the hypothetical scatter plot. If we adopt the criterion of minimizing UI, figure 3.1, this one, shows that the residual UI2 and UI3 as well as the residual UI1 and UI4 receive the same weight in the sum. So when we sum all of these residuals, although the first two residuals are much closer to the sample regression function than the later two. In other words, all the residuals receive equal importance no matter how close or how widely scattered the individual observations are from the sample regression function. A consequence of this is that it's quite possible that algebraic sum of UI is small, even zero, although the UI widely scattered around the sample regression function. So, for example, we can give the values. For the y1, we can give 10, y2 minus 2, y3 minus 2, and for the y4 minus 10. So when we add them up, we will see that this will add them sum to 0. The algebraic sum of the residuals is 0, although y1 and y4 are scattered more widely around the sample regression function than y2 and y3. We can avoid this problem if we adopt the least square criterion. So we put square in order to obtain not zero values for our summation. So as small as possible where y are squared residuals. By squaring y, this method gives more weight to the residuals such as y1 and y4. So the first purpose is not to obtain the zero distance. The second one, we are giving more weights to the big residual values. For example, we are giving more values or weights to the y1 and y4 by using square criterion. So from figure 3.1, then residual y2 and y3, as noted previously under the minimum y criterion, the sum can be small even though y are widely spread out sample regression function. But this is not possible under the least square procedure. For the square y in absolute value, the larger the sum of y square. A further justification for this square method lies in the fact the estimators obtained by it have some very desirable statistical properties, as we shall see shortly. Now we will see some basic properties of the residuals and the OLS estimation. So as I have noted above that y square is a function of beta 1 and beta 2. That is the sum of the squared residuals is some function of beta 1 and beta 2 for any given set of data. Choosing different values of beta 1 and beta 2 will give different y's, and since different values of y square. To see this clearly, consider the hypothetical data on y and x given in the first column. So this is the actual values, and these are the independent values. This is the dependent value, actual dependent value. This is independent values. So we are obtaining for the first one, the intercept value is 1.5, and beta 2 is 1 and 3.1.35. This is our first equation, and this is the second equation. So from the first equation, let me show it from here again. This will be the first equation, 1.5, 1.3. So this is 1.5, and this will be plus 1.3. xi, yi hat. So the other one is 3 plus 1. So the other one is this one. Now this is starting from 1.5. The other one is starting from 3. So let me make it a green line. But the slope parameter is smaller than 1.3. So it can be like this. So 3 plus 1 xi y hat. So by using these two sample regression function, this is sample regression function 1, this is sample regression function 2. He is obtaining the residual terms. For this one, it's obtaining like this. And for this one, it's obtaining like this. This is uy1. This is uy2. This is uy3. And this is uy4. So let me show from the table. So by using this computation for the first one, so let me skip this one and show from here. So for the first uy1, he obtained 2.9, y2 7, y3 8.3, y4 9.7. For the second one, it obtained y1 1, 0, y2 minus 2, y3 minus 1, and for pardon me, these are the y's. So let me write it again. This is y1 and y4. So these, for the first computation, these are the y's. So from these computations, y computation, they obtain 0. Look, this is 0. And for the second one, again, they obtain 0. So hypothetically, we see that these will be 0. So for the second criterion, we put squares. For the squares, for this one, they obtained 12.2. For this one, they obtained y2 equals to 14. So distance 1 is smaller than, this is distance 1, smaller than distance 2. So what we have called for this criterion, if distance 1 is smaller than distance 2, so we will select this set of parameter values. For beta 1, we have to select 1.5 and we have to select 1.3 for beta 2. So ordinary least square methodology gives this principle to us that if which one is smaller than the other one, then select the smallest one. So this is the ordinary least square principle. So to see this clearly, consider the hypothetical data y and x given in the first column, table 3.1. Let us now conduct two experiments in the experiment 1. Let beta 1 1.5 and beta 2 1.3. Let us not worry right now about how we got these values. Say it's just a guess. It's an example. Using these beta and values and the x values given in column 2 and table 3.1, we can easily compute the estimated yi. We estimate the yi's. And now let us conduct another experiment, beta 1, 3, beta 2, 1. The estimated values yi from this experiment are given, yi2 in column. Table 3.1, since the beta values in two experiments are different, we get different values for estimated residuals as shown in table y. Are the residuals from the first experiment and y2 from the second experiment. The square of these residuals are given in columns 5 and 8. Obviously, as expected from equation 3.1.3, these residual sum of squares are different since they are based on different set of beta values. Now, which set of beta values should we choose? Since beta values of first experiment give us a lower sum of square residuals, 12.2, than the obtained from the beta values second experiment, 14, we might say that the betas of the first experiments are the best values. But how do we know? For if we had infinite time and infinite patience, we could have conducted many more such experiments choosing different sets of betas each time and comparing the resulting sum of squares and then choosing that set of beta values that gives us the least possible value of sum of squares residuals, assuming of course that we have considered all the conceivable values of beta 1 and beta 2, but since time and certainly patience are generally in short supply, we need to consider some shortcuts to trial and error process. Fortunately, the method of least squares provides us such a shortcut. So, in order to use a trial and error process, we have to use lots of different beta 1 and beta 2 values. In order not to use this time-consuming approach, we have to use a more or a better methodology, a shortcut methodology. The name of this shortcut or better methodology is the method of least square. So the principle or the method of least squares chooses beta 1 hat and beta 2 hat in such a manner that for a given sample or set of data, sum of squared residual is small as possible. In other words, for a given sample, the method of least squares provides us with unique estimates of beta 1 and beta 2. So, by using this simple methodology, instead of using lots of trial and error method, we are directly obtaining the beta 1 and beta 2 by using this least square methodology, ordinary least square methodology. So, as I told you before, we are getting the, let me show. We are getting the partial differentiation of this sum of square residuals and equate it to 0, and we are again getting the partial derivative with respect to beta 2 and obtain the second normal equation. So this will leads to normal equation 1 and normal equation 2. So as all you know that if we equate a derivative to 0, this means that there is no change in the curvature. So this is delta change in x, delta change in y is equals to 0. So you can obtain this point by using this delta changes. So there is no change in this part. So this is giving the optimal xi. So if we get the partial derivative, we will obtain the place of beta 1 and we will obtain the place of beta 2. So these are, by using this methodology, we will obtain these two normal equations. From these normal equations, you can derive the beta 1 and beta 2 formula. So this is the beta 2 formula and this is the beta 1 formula. Okay, let me stop the first class here. 10 minutes later we will start the other